Strength of cement. After the process of hydration of cement, it starts gaining some strength due to the different chemical reactions that occur during like that of the different chemical compounds like tricalcium silicate, tricalcium aluminate and tetracalcium aluminoferrate react with water to form to contribute differently to the strength of concrete. On adding water to the cement, tricalcium aluminate is the earliest to hydrate and contributes to the strength of cement paste at 1 to 3 days age. But at the advanced age, it causes retrogression in the development of strength, particularly in cements with high content of tricalcium aluminate. Due to the development of large amount of heat of hydration, it causes cracks in the paste and disintegrates the hardened paste or concrete. Although tricalcium aluminate is least desirable in cement, but it acts as flux for the fusion of clinker and reduces the temperature of fusion, resulting in saving of fuel during the manufacture of cement. It also facilitates the combination of lime and silica, and increase in iron content decreases the percentage of tricalcium aluminate, but it causes higher formation of tetracalcium aluminoferrate. A low tricalcium aluminate generates less heat and develops higher ultimate strength and exhibits greater resistance to the destructive elements than cement containing a higher percentage of tricalcium aluminate. For this reason, tricalcium aluminate is very useful in the manufacture of cement. Tetracalcium aluminoferrate, it is considered as inert material, but it also acts as a flux for clinker fusing at lower temperature, resulting in saving of fuel. Practically, there is no, it does not contribute to the strength of cement. Now, what about the contribution of tricalcium silicate? After adding water to the cement, tricalcium silicate hydrates immediately next to tricalcium aluminate and contributes early strength to the cement paste or concrete. In general, the early strength of Portland cement will be higher with higher percentage of tricalcium silicate. Many researchers have found that tricalcium silicate contributes most of the strength development during the first 4 weeks. The 7-day strength of tricalcium silicate has been found about 400 kg per centimeter square, and 18 months strength has been found out to be 700 kg per centimeter square. When we talk about the dicalcium silicate, the gain in strength of dicalcium silicate has been found after 28 days onwards after adding water to the cement. At 7 days strength, no strength develops due to the dicalcium silicate. That means the dicalcium silicate compound does not contribute much to the earlier strength as compared to that of tricalcium silicate. But if we talk about the later strength, dicalcium silicate is the main compound causing the later strength of cement. At the age of about 1 year, weight of the tricalcium silicate contributes very less as compared to that of dicalcium silicate to the later strength. Dicalcium silicate has found to develop greater strength after 18 months, and dicalcium silicate has been found to develop about 700 kg per centimeter square of strength. The development of strength of different compounds has been discussed, and now we will talk about heat of hydration or hydration of cement. The hydration of cement is accompanied by liberation of heat. Such a chemical reaction is known as exothermic, and there are many exothermic chemical reactions. Normal cement generally produces heat of hydration about 90 calories per gram in 7 days and 90 to 120 calories per gram in 28 days. As the conductivity of concrete is very low, it acts as an insulator, and the interior of a large mass of concrete such as dam, hydration of cement can develop very high temperature. At the same time, heat dissipation takes place from exterior surfaces of the concrete, and steeper temperature gradient develops. During further cooling of interior causes serious cracking of concrete. It has been found that in cold climates, heat produced by the hydration of cement prevents freezing of water in the capillaries of the fresh concrete. In such situation, high evolution of heat is advantageous. Strictly speaking, the heat of hydration is a composite quantity consisting of chemical heat of reaction of hydration and heat of absorption of water on the surface of gel formed by the process of hydration. The heat of hydration absorption being about 25% of the total heat of hydration. From practical considerations, total heat of hydration is not important, but the rate of heat evolution is important. This was about the heat of hydration. Now we have the setting and hardening of cement. Term setting is used to describe the stiffening of the cement paste. Broadly speaking, setting refers to a change from the fluid and rigid state. On adding sufficient amount of water to cement, a paste is formed which gradually becomes less plastic and finally becomes stiff and hard. When the paste has lost its plasticity and becomes sufficiently rigid to withstand the arbitrarily defined pressure, then the paste is said to have set. The setting period has been divided into two groups known as initial set and final set. After the final set, the cement paste further increases in strength and rigidity. This state of paste is called as hardening of the cement paste. The setting process is accompanied by temperature change in the cement. The initial set corresponds to the rapid rise in the temperature and final set to the peak temperature. The setting time of cement is found to decrease with high rise in temperature. Now this setting time cement set can be divided into two groups, the flash set and the fall set. When we talk about flash set, if on adding water to the cement, a very violent reaction takes place with the evolution of large amount of heat of hydration and cement sets within 5 minutes after adding water to it. This set is called as flash set. And if the abnormal premature stiffening of cement occurs, this is called as fall set. Fall set is basically the abnormal premature stiffening of cement paste that takes place in few minutes after mixing water with the cement. In this case of fall set, no appreciable heat is involved and remixing of cement paste without adding any water and restoring plasticity of cement is possible until it sets in the normal manner and without any loss of strength. Now what are the causes of fall set? If gypsum is added and underground is very hot clinker, the dehydration of gypsum takes place and lime hydrate CaSO4 0.5 times H2O or anhydride CaSO4 are formed. When water is added to such cement, these hydrates form gypsum and plaster set takes place, resulting into stiffening of the paste. If alkalis are present in the cement during storage period, during the storage period, then they form alkali carbonates. These alkali carbonates react with calcium hydroxide liberated by the hydrolysis of tricalcium silicate to form calcium carbonate. The calcium carbonate participates and produces rigidity in the paste. Okay, then we have effect of alkalis. Increase in strength beyond 28 days is strongly affected by alkalis. The greater the amount of alkalis present, lower the gain in strength. Thus, the amount of alkalis should not be more than 0.4%. That means the alkalis alter the strength of cement very badly.